Let's recall L'Hopital's rule. Which I'll abbreviate L'H. If we're looking at limit as x approaches a of f of x over g of x, and this function has indeterminate form at x equals a, suppose the indeterminate form is 0 over 0. Now there are other indeterminate forms for which we can use L'Hopital's rule, but for this case we're going to assume our indeterminate form is 0 over 0. Then we look at the limit as x approaches a of f prime of x, that is the derivative of the numerator, over the derivative of the denominator, so that's g prime of x. If this limit is equal to L, and L could be a finite number or infinity or minus infinity, as long as it's not an indeterminate form, that implies that the original limit as x approaches a of f of x divided by g of x also equals to L. Notice that we are not using the quotient rule of differentiation. It's just the derivative of the numerator over the derivative of the denominator. So we're going to look at 3 examples where we have indeterminate form 0 over 0, and we're going to solve them by using L'Hopital's rule. The first one is a familiar example. We used this many times. We derived it using geometry and trigonometry. That is, limit as x goes to 0 of sine x over x. We know that this limit is equal to 1. Let's verify it by use of L'Hopital's rule. So limit x goes to 0, sine of x over x. This gives us this indeterminate form 0 over 0, because as x approaches 0, so the sine of x, and of course in the denominator x goes to 0. So we can use the L'Hopital's rule, and that means we look at the limit as x approaches 0 of derivative of the numerator, that is cosine of x, divided by derivative of the denominator 1, that just is the limit x approaches 0 of cosine of x, and that cosine is continuous at x equals 0, so this is equal to cosine of 0, which of course is 1. And so we verified the result we already knew by L'Hopital's rule, that limit as x approaches 0 of sine x over x equals 1. Now in part B we'll look at slightly more complicated problem, but not too much. Part B, we want to evaluate the limit as x approaches 0 of sine of 10x divided by 5x. Again, as x approaches 0, we want to see if this function is continuous at 0, so that the limit and the value of the function at 0 are the same, but it isn't. So the numerator approaches 0, the denominator approaches 0. We apply the L'Hopital's rule and look at the limit x approaches 0 of the derivative of the numerator, which is 10 times cosine of 10x, divided by the derivative of the denominator, which is 5, and that's limit x approaches 0 of 2 times cosine of 10x. As x approaches 0, so does 10x, so this is 2 times cosine of 0, which is equal to 2. Again, one application of L'Hopital's rule, and the problem is solved. So let me summarize that here. The limit as x approaches 0 of sine of 10x divided by 5x is equal to 2. Let's go to part C. And part C is slightly more complicated problem. In part C, we want to evaluate the limit as x approaches 0 of sine of 3x plus tangent of x squared plus x, and in the denominator we have 3x squared plus 2x. So once again, let x go to 0, sine of 3x goes to 0, tangent of x squared plus x also goes to 0, numerator approaches 0, and clearly the denominator also approaches 0. We have the indeterminate form 0 over 0. So we can apply the L'Hopital's rule and evaluate the limit as x approaches 0. Derivative of the numerator is 3 times cosine of 3x plus 2x plus 1 times secant squared of x squared plus x. And in the denominator, we get 6x plus 2. Now, as x goes to 0, you can see that the function now does not give us indeterminate form 0 over 0. 3 times cosine of 0 is 3, and 2 times 0 plus 1 is 1. Secant squared of 0 is also 1. So in the numerator we get 3 plus 1. In the denominator we get 0 plus 2, which is 2. And the final answer is 4 divided by 2, which is 2. And so again, in conclusion, the limit as x approaches 0 of the function sine of 3x plus tangent of x squared plus x divided by 3x squared plus 2x is equal to 2 by using L'Hopital's rule. For more videos, visit www.mathprepvideos.com.